Earth has recently been confirmed to have a new long-term companion in space. Not a second moon, but a small asteroid known as 2025 PN7. This object shares Earth's orbital period around the Sun, placing it in a rare configuration called a quasi-moon. It will remain near Earth for several decades, not because it is gravitationally bound to us, but because its orbit closely matches our own. The discovery comes from routine sky surveys and careful orbital analysis, adding a new data point to our understanding of near-Earth space. In this video, we will explain what was discovered, why it matters scientifically, and what it tells us about Earth's orbital neighborhood. Let's get started. The asteroid designated 2025 PN7 was identified through routine sky surveys that repeatedly image the same regions of the sky over long periods. These surveys are designed to detect faint, slow-moving objects whose motion only becomes apparent when multiple observations are compared. In this case, the asteroid did not stand out because of its brightness or size. It is only about 19 meters across, but because of how consistently its motion matched Earth's. When astronomers calculated its orbit, they found that 2025 PN7 completes one revolution around the Sun in nearly the same amount of time as Earth. That shared orbital period is the defining condition that distinguishes quasi-moons from ordinary near-Earth asteroids. Rather than passing through Earth's vicinity and continuing onward, this object remains nearby because its motion stays synchronized with Earth's year. From Earth's perspective, this synchronization creates the appearance that the asteroid loops around our planet. In reality, Earth and 2025 PN7 are independently orbiting the Sun, but their nearly identical timing causes their relative positions to change slowly. This produces complex, repeating motion patterns that can persist for many years. Once enough positional data was gathered, astronomers ran orbital simulations, both backward and forward in time. These models indicate that 2025 PN7 has likely occupied its current quasi-satellite state for several decades already. Projections show that it will remain in this configuration until roughly the early 2080s, after which gradual gravitational influences are expected to shift it into a different orbital path. The confirmation of 2025 PN7 does not represent a sudden arrival or a new development in Earth's environment. Objects of this size are difficult to detect unless viewing conditions are favorable, and many similar bodies likely go unnoticed. This discovery reflects improvements in detection sensitivity and long-term tracking rather than a change in Earth's surroundings. Importantly, orbital models show that 2025 PN7 poses no risk to Earth. Its path remains well outside any scenario involving atmospheric entry or impact. The significance of the discovery lies not in proximity or hazard, but in classification, identifying another stable example of an Earth co-orbital object. Each confirmed case adds to a small but growing sample that allows astronomers to refine how these objects are detected, categorized, and tracked. 2025 PN7 is now one of the clearest examples of how timing alone can keep a small body near Earth for decades. Quasi-moons occupy a narrow and delicate orbital state, governed by resonance rather than capture. In the case of 2025 PN7, its orbital period matches Earth's closely enough that gravitational interactions repeat in a predictable pattern. These repeated interactions gently shape the asteroid's motion without pulling it into a true orbit around Earth. This type of resonance is scientifically valuable because it allows researchers to study orbital stability in real conditions. Small deviations between predicted and observed motion can reveal the influence of subtle forces that are otherwise difficult to measure directly. One of the most important of these is the Yarkovsky effect, in which uneven heating and cooling of an asteroid surface produces a tiny but continuous change in momentum. Over long timescales, even forces this weak can alter an object's trajectory. By tracking quasi-moons over decades, scientists can test how accurately these effects are modeled and how they influence orbital evolution. This makes objects like 2025 PN7 particularly useful for validating long-term predictions. There is also active interest in where Earth's quasi-moons originate. Some may be fragments from the main asteroid belt that gradually migrated inward through gravitational interactions. Others could be debris created by ancient collisions involving Earth or the Moon. In at least one previously studied case, spectral measurements suggested similarities between a quasi-moon and lunar material, raising the possibility that some of these companions are remnants of past impacts. For 2025 PN7, its small size and faintness currently limit what can be determined about its composition. However, its stable and predictable orbit makes it an ideal subject for continued observation. Even without direct sampling, precise tracking over time can reveal how resonant states form, persist, and eventually dissolve. Beyond Earth, these studies have broader implications. Resonant companions are expected to exist around other planets, including potentially around Earth-like planets in other star systems. Understanding how such configurations behave helps astronomers build more accurate models of planetary systems as a whole. In this sense, quasi-moons provide a bridge between theory and observation. They allow scientists to test abstract orbital models against real objects whose behavior can be measured over human timescales. One of the most practical consequences of a long-lived quasi-moon is accessibility. Compared to many near-Earth asteroids, objects in Earth-like orbits tend to have lower relative velocities. This means that reaching them with spacecraft would generally require less energy than missions to faster-moving targets. Although no mission is currently planned for 2025 PN7, objects like it are frequently discussed as potential candidates for future exploration. They offer opportunities to test navigation systems, autonomous guidance, and close proximity operations around small bodies, all of which are essential capabilities for future asteroid missions. From a planetary defense standpoint, quasi-moons also improve modeling accuracy. While 2025 PN7 itself is not hazardous, understanding how objects evolve in Earth-like orbits helps refine predictions for other near-Earth asteroids. Improved models lead to better long-term assessments of how objects transition between different orbital states. There are also implications for understanding Earth's immediate space environment. Studying quasi-moons helps researchers examine how dust and small debris behave near Earth's orbital path. This contributes to models of meteoroid streams and improves predictions about the distribution of material in near-Earth space. Looking ahead, continued monitoring of 2025 PN7 will allow scientists to observe how gradual forces influence its motion over time. Because its departure from the quasi-moon state is expected to be slow, it offers a rare opportunity to observe orbital evolution directly rather than inferring it solely from simulations. As detection techniques improve, it is likely that additional quasi-moons will be identified. Each new example will help clarify how common these configurations are and how long they typically last. – 2025 PN7 is not a second moon, but a small asteroid sharing Earth's orbit through precise timing rather than gravitational capture. Its long-term presence helps scientists test orbital models and understand how small bodies behave near Earth over decades. Quiet discoveries like this refine our picture of Earth's dynamic neighborhood in space.